I'm Giacomelli, and I'm really pleased to be here today. And one of the primary reasons I'm pleased to be here today is to see all of you talking about agriculture. Agriculture and food production is, again, important, has come to the top of the list. And we all have to eat. We talk about energy for our cars and for other activities. We need energy for us too. And I enjoy eating at least 3 times a day. So let's move on with that. I am a faculty and director at the Controlled Environment Agriculture Center at the University of Arizona. And that's an interdisciplinary group of faculty and staff and students that work on controlled environment problems, trying to educate people, trying to create more information, do research, and then to outreach that information to those for the future. This is my abstract that I put in the report. This will be up online at some point, so I figured people may want to know what I was supposed to say. And now you can hear what will come out at this point. ACES comes back again. Casey Ting gave you an introduction into that. Fundamentally, automation, culture, and environment integrated into a system will allow you to grow a plant anywhere you want, any plant. Now, we have to think about that in terms of economic terms. But I'll give you the example that you saw earlier today. If you remember Jen Nelkin's presentation, she went through in several of her slides the thought processes for automation, culture, and environment to put her system together. And obviously, she did something very, very, very right. What I want to do today is evaluate or give you information about 2 existing operating systems and give you some examples of its parameters, which we can evaluate them. They're very similar. They're producing plants in a controlled environment using hydroponics. Primary purpose is for food production, but also potentially a better quality of life, particularly at South Pole, and ultimately to establish some outreach and educational opportunity using this technology. The take-home message. Here is normally the last slide of the presentation. Take-home message. 10 to 13 grams of edible biomass, wet weight, per kilowatt hour. It's a number. It's a number that we're comfortable with. It's a number that we've calculated and determined and measured in these systems. So that's edible grams of fresh weight produced per kilowatt hour of electric power. And what are we talking about? The electric power, primarily lighting in both of these systems, which require about 70%, 70% of the energy. But also we need power for environmental control and for monitoring and services. This is a polyculture system, meaning multiple crops. What I tell students and growers never to do, to put different crops in the same environment, in the same hydroponic system. But we had little choice. You deal with what you're given and you do the best you can. So this is not maximizing productivity, but it is a target on the wall. And I'll show you how we got to that point. 2 examples, the South Pole Food Growth Chamber and then the prototype Lunar Greenhouse. One thing you can do to make life easier for yourself is to tackle a problem where there really is no competition. So you go down to the South Pole and say, well, how much is it going to cost to produce the food? And they really don't argue too much. Neither does NASA about going to the moon. No, we'll take what we can get, but let's be realistic here. It is a tough situation, and it does shut things down for people who live and work at the South Pole. And some numbers, a little bit chilly, minus 61 Celsius. Coming from Tucson, Arizona, where the unit was built, where we're above 38 degrees Celsius on many times, probably still today. Going down to the South Pole, all points face north. You leave and you can't get away. You got to go north. But it is a frozen, arid desert, and we lived in a hot desert, dry desert in Tucson, Arizona. So some similarities. Here's a picture. You're standing in the environmental room, looking straight forward into the food growth chamber. And off to the right is, in the same room as you, a hobby hydroponic system where you can begin to learn about how to grow crops hydroponically. But the food production room is separate from glass walled, so you can have climate control and less interruptions of the productivity. I'll do very little of this. It will be documented in the presentation, but Raytheon Polar Services was the contractor through the National Science Foundation, and in the year 2000 we wrote a proposal and won the grant, won the contract to build this facility. And Martin Lewis and Andy Martinez are the recent people working with Raytheon and now Lockheed Martin, who we worked with and followed up on operations, so that we help continue with the unit. Phil Sadler needs to be mentioned here about his creativity, his vision, his expertise in understanding what is needed for a system to work, quote unquote, on the ice. And he manufactured the nutrient delivery system, the HVAC system, the water-cooled lamps, and the plant growth trays. Obviously, we had other people at the University of Arizona working with us, and they're listed here. Expectations of the deliverable. Well, the idea was that it was a machine that would produce fresh vegetables, and this was in 2001. It arrived in 2004. It had to have some energy efficiency. It's difficult down there for bringing in fuel. Resource conservation, so recirculating hydroponics. User-friendly operations and maintenance, so that it could be run by those who were on site initially as volunteers, not trained in any way. Minimum assembly, offer the passive use for therapeutic value, green space visibility, and it had to be integrated within the new station. The room was set aside for this device to be put in, and it had to fit through a door not much larger than what you walk through getting into this room. Here's a model of it. You see the station hallway in the far back. You step into the environmental or the enviro room, and in front of you is the glass wall and the production room. If we look on the right, it's about 57 cubic meters in volume, about 23 square meters of growing area. Tall crops could be grown in the center, seedlings and herbs up on the wall, leafy crops at 2 levels on movable troughs. From a top view, plant growth room, the environmental room, and using some space for utility room. Some of the initial crops and production rate, 10 kilos per week of lettuce, herbs, and greens, and then in tall crops, tomatoes, cucumbers, and sweet peppers. They've gone on to grow more than 50 different species of crops in the system. Again, one environment, and I did mislead you a bit. There are 2 possible hydroponic nutrient solutions that we could have, all recirculating to save water. This is Lane Patterson, was the first operator to, once it was put together down at South Pole, to make it work. And here he is standing, give you some scale of the 23 square meters. Design solutions use the high-intensity water-cooled lamps, part of NASA-supported project, the double-pass growing tray, and the automatic monitoring and control system. And I'd like to show you that in these next slides. The lamps, the 2 rows of 6 lamps, water-cooled, 1,000 watt, high-pressure sodium, providing about 400 micromoles per square meter per second at the tray level, about 1 meter off the ground. Lane giving us indication that with the tall crops in the middle, the 1 row of lamps would light one side and the other row of lamps would light the other side, irrigating the crops and the leaves with light, trying not to have any of it hit the ground, obviously once the plants got larger. The water-cooled lamp was the key to it. It allowed a 1,000-watt lamp to be touched with your finger like this and not run off scared or hurt at this point, nor having the plants burned in any way. It's just an off-the-shelf 1,000-watt lamp put in a double-walled glass water jacket that was able to remove 60% of the heat that the lamp would put out into the system, which obviously allowed us to reduce the HVAC system And it allowed the fact that the plants could grow right up to the lamp. It was only roughly a 2.5 meter tall, 2.8 meter tall structure, so there wasn't a lot of room. There's Phil next to his creation and the sliding in and out of the hydroponic system. And you see the trays lined up. It's a nutrient film system. And there's Lane demonstrating the 3-part tray. The seedlings are transplanted to the top of the tray. There's a false bottom, and then there's the full bottom. The idea is that the water would enter at his hand, flow down the top false bottom, flow into the bottom, and then be discharged at the same side of the row that the water was added. And it was sized to be able to fit into the machinery that could wash it automatically at the pole. I'd like then to move to the Lunar Greenhouse. And the objective here is to develop a system that, with some fidelity and size, could offer bioregenerative life support, or at least the biology, demonstrate the biology of the life support and then sitting in a laboratory at the University of Arizona. The unit is about 18 feet long, 5.5 meters, and 2.1 meters in diameter, just under 8 feet, lit with the same lamps in a hydroponic system. This was a size that we need to demonstrate, and we are in the process of doing that now, that all of the oxygen, all of the water necessary to support one astronaut, one person, could be provided on a daily basis through the system. And about 50% of the food calories could be provided with this volume of production in a hydroponic system. Here we are with the end view on a very good day. That should be every day. It takes a while to get to this point, of course. And then you reach a steady state condition, and what we would do then is monitor the input and the outputs. And Dr. Kozai this morning mentioned about the resource utilization efficiency. And here is really what we're doing. We're just monitoring energy, water, nutrients, carbon dioxide, and labor that goes into the system, and looking for these 3 critical components coming out and trying to determine some efficiencies. Some of the University of Arizona team working on it, as well as our international team of Italian aerospace companies, Aerosecure and Thales Alenia. Some numbers that will be here available to you. It's also online. May not mean too much at this point, but there's numbers. Biomass increase, 60 grams per day, wet weight. The entire unit was on load cells, so we could know weight every day in real time. Water production, 21 liters per day. Of course, you have to know how many plants are in there. But water consumption, 25 liters per day. We lost some. We're not sealed very, very tight, not full tightness for sure. CO2 consumption, 20.22 kilos per day. Electric power, big one, 100 kilowatts per day with lighting and pumping requirements. This number, 24 grams of biomass per kilowatt hour, includes edible and non-edible. The number I gave you in the first slide was 10 to 13. That was edible wet weight biomass. This is total wet weight biomass. And if you can enjoy eating roots, go at it. You can do that too, or tomato leaves and along the line. And then we looked at labor demands. It's not too pertinent at this point in time, but we did look at it. When you contrast the two, here's the 2 edible biomass numbers, the 10 and the 13. One came from the South Pole, the other one came from the Lunar Greenhouse. I'm glad they're at least in the same order of magnitude. Pretty close. Can they be improved? Absolutely. It's a target. We need to make it better. Again, this was a production facility, not a research facility to optimize growth. But this is a level that can be done today by those not experienced in production systems of controlled environments. The lighting system, the nutrient delivery were similar, multi-cropping or the polyculture system, and telepresence systems and procedures. The fact that we did not have to be at the South Pole, I've never been there, but I've been there virtually. I can see it, I can get the information. We have information that we provide every week in review of how it's operating. You're welcome to look back on this. This is the details for the horticultural and plant people of how it was done. It's all there. There's publications out there too as well, but I'm not going through that at this point. The two focus items that are the water-cooled lamps and the cable culture hydroponic. That lamp made it possible. High pressure sodium obviously will not be around forever. LEDs are coming along. They needed to eat for the past 10 years, so they got the high pressure sodium. Let's put water cooling on LEDs and move ahead. Then the cable culture hydroponic, a lightweight nutrient film technique, more or less. Alan Cooper would cringe if he heard me say that, because it's a vertical system, not a horizontal, which is NFT. But it works very well, lightweight, grows the plants. Finally, concept of evaluating and keeping in contact with sensors of the system. Dr. Kachira and his graduate student David Story are continuing with work that's done on decision support systems, that is taking information, evaluating them, and you've heard this already from a number of speakers. The data is not important, it's what the data tells you is important, and then if this can be done in an automated, non-invasive way, then your operators, those who have to make the system work, can benefit from this. And that's what's their work. Here is a projected screen of information that can be provided for us. We need a lot of research information. A grower would look for other specific things. And of course, this can be made a lot more friendly, but the information is here. It's here and is now, and we can go and see it in a few moments. It's particularly interesting to us is the live camera that's available, and then the spectral, hyperspectral studies that can be done using other cameras, and Dr. Kachir and his students are continuing to work on that. That can give us some non-destructive, non-invasive information about how the plant is surviving, how it's growing, how it's developing, and then that leads us back to improved climate control. And then the number of people that have worked on the Steckler project over the past few years, but the Lunar Greenhouse and the Moon project over the past 12 years. Finally, education. We had a great opportunity to take one of these systems. Well, you see Lane Patterson standing in the lab giving a tour. We do it all the time. We do classes with a web camera from our laboratory, but we could never take it on the road, and we had an opportunity to build one that could go on the road. So one unit showed up in San Diego this summer for a month in front of hundreds to tens of hundreds of thousands of people, I understand. And another one sits today in the Chicago Museum of Science and Industry for several months, where many people can come through inside and see hydroponics, controlled environments, and see it in an application that they see a future, to go to the moon and Mars. But then we relate it back to the fact that we need to eat here and now, and these systems came from hydroponics and controlled environments that we've known for a long time and have worked with on Earth, and now are producing commercially viable production systems for helping to feed people and providing good nutrients and good quality of life for people. We'll bring it back to Earth again, and then it will go back to the moon with new technologies along the way. And those involved with that have to be given their credits here. Finally, did I say finally for 3 times already? Yep, 5 great challenges. I threw these together because I hear them a lot. Or maybe it's just the voice in my head. Know your market and your market value, which says know what you're competing against before you build a system to try to sell a product if you want to be profitable. Be educated, have experience. Climb the learning curve as fast as you can. Support your local university, particularly one with controlled environments. Sorry, Sanjeev, I had to do that. Compliance with the situation, and I initially thought of make sure you know your local code officer and listen carefully, but it's not just code, it's the laws of nature, and we've heard people talk about that. Mr. Todd mentioned that. Follow the laws of nature, and that was number 5 I put. Allow biology and physics to do the work for you, not work against you. And number 4 that I skipped, have some metrics that give you an impression of how many kilowatt hours per gram do I need to produce. That is, know those resource use efficiencies that Dr. Kozai talked us about, output-input ratios. And with that, I would like to say that I appreciate the opportunity to speak today, and I look forward to the continued discussions that will rest of today and tomorrow. And I thank you very, very much.
Who has a question for the speaker?
Hello? Is this... Okay. Great talk. I was wondering how that environment works in a zero-G situation. How does everything stay in place?
Very good question. I misled you if you assume that this would go in zero-G. This will always be on a planet, Mars, Moon, asteroid. Only works with at least some gravity. We want the laws of nature to help us move that water. Good point. Thank you.
Next question.
You mentioned that one of the requirements was to be used for therapeutic uses and green space visibility. And I was just curious with that setup, it didn't appear that there was much space for people to go in there and actually use it for that purpose. And then the following question that is, are you doing any studies that include what people are doing in terms of therapeutic? Are they going in there, spending time in there? What are they doing? Do they have any like surveys of their enjoyment levels of the different tasks?
Yeah, good question. It is a small space because it's valuable space. It's only about 100 square feet, so 10 square meters, more or less. And actually, I argued against having that much because I wanted more production space. But that's what happens, engineer, horticulturist. But the locals love it. They go down there, they have internet access, they have a phone there, they have a table, they enjoy wine you can sign up to have a date down there if you wish, and have a candlelight dinner. And the top question every year is if there was something that had to leave the station that we couldn't afford to support anymore, the bowling alley or all the things that go on, the art classes and stuff, the first thing that they said that has to stay there is the plant growth. Right. Absolutely. It's a green space, 2 colors in Antarctica, white and black, basically. 2 primary smells, body odor and diesel fuel. Diesel is to run the generators. And by the way, I didn't mention the fact that it's equivalent to about $50 per pound of vegetable crops that come out of South Pole. And that's because of the cost for the diesel fuel to be down there. Having said that then, it's not a fair comparison to use that number. Use the other number that I talked about. Find better fuel. Sure. And then does $50 mean too much when there's no other choices for 800 miles? Probably not.
We have 2 more questions.
Could you speak specifically to the carbon dioxide and oxygen sensing and management?
Okay, carbon dioxide and oxygen management. We don't manage the oxygen. We are leaky enough that we don't go over 22%. Not really a problem. CO2 management, we pump about a 1,000 psi cylinder a month into the South Pole to keep the plants growing, so about 220 grams per day. And that's what makes it go, for sure. We do have a high level CO2 alarm at 2,000 ppm. Warning at 10,000 ppm, it gets louder, and they want everybody out at that point. So there's that safety concern.
Sanjay.
Okay, so Gene, thanks for giving a really nice metric. I think roughly speaking, order of magnitude, I heard 10 grams per kilowatt hour as one number. So it's a great number because it's at the micro scale, right? We heard some larger sort of facility costs in millions of dollars. So I was just trying to think about, you said this needs to be improved. I was just trying to think about how much it needs to be improved. So I did a couple of quick calculations, and here's what I came up with, that the energy cost alone okay, of growing 1 pound of arugula would be about $4. Given 10 cents per kilowatt hour and 10 grams of some leafy produce, it's mostly leaves and not much else, we're talking about, let's just say, in round numbers here, right? Did I get it wrong? I mean, you know, the thing here is that.
You're pretty close, yeah.
Okay, so
yeah.
a pound of arugula is, I don't know what. I don't know what. It'd be somewhere around there, around $4, $5, depending on where you get it. But the point here is, if you think about this economically, and maybe you've thought about it, do we need to go down by a factor of 5 or 10 or 100 for this thing to be viable on a scale where it's not the NASA motivation, it's a more general motivation?
Yeah, exactly. Certainly an order of magnitude would be in order here, for sure, to attempt to do. Fundamentally, though, these numbers, as I said, I did couch them by saying that they can be improved. I don't know they can be improved by a factor of 10, but that's the challenge. I would bet that we could improve them by a factor of 2 or 3, almost immediately, by the way it was operated. If it was operated more as a production system with out-of-pocket costs, as opposed to being a system that is used as a piece of hardware to grow crops. And the last thing, if I could, that was shown on there, it's not up there now, Plant Lab's up there, was the actual live picture of the Lunar Greenhouse. So we could have gone there, we could have seen information and take a look at and watch the plants grow.
What's the URL? What do I Google?
Oh, you can look up Lunar Greenhouse, Arizona, and you'll come to the website, which gets you right to there, and all the information about the Lunar Greenhouse.
Thanks again.